We're continuing looking at discrete time convolution, and I've got another example. So here's the example. Determine the response of an LTI system whose impulse response, h of n, and input x of n are given by, and then I've got the mathematical descriptions of those responses there. So amidst all this math, it's very easy to lose sight of the engineering that we're doing. So let me again remind you that we've got some sort of system here that's linear and time invariant. So this could be a circuit, this could be a mechanical system, whatever, as long as it's linear and time invariant. What we're trying to determine is if I put in the signal x, which is this alpha to the n u of n, which I'll plot in a second, what do I get out? That's the question, right? So if you're thinking of this as a circuit, you know, maybe this voltage or this current is coming from an antenna. So I put in this signal or whatever. I want to know what do I get out? So what's the output? You know, across the capacitor or whatever. Now you have to tell me something about the system more than that. It's just linear time invariant, and we do, right? We tell you that when you put in an impulse to the system, you get out this thing, the unit step, which is the impulse response. So this is like a little experiment. You put a little disturbance into the system, and that's the impulse, and then this is what you get out. So now, knowing that piece of information, that little experiment result, I can get the output. I can answer my question by performing this operation. This is the convolution operation. I'm going to take the input, convolve it with the impulse response, and that will give me the output. That's the engineering part of this. Okay, now let's actually do it, with mathematics. So if I look at the convolution sum, the x's appear with k, and the h also appears with k, albeit a minus k. So one strategy I have is to plot x versus k. So all I'll do is replace n with k. So alpha I have here is a real constant between 0 and 1. So as a constant between 0 and 1 goes to the kth power, it gets smaller and smaller, right? Think about 1/2 to the 1, 1/2 to the 2, 1/2 to the 3. So when k is 0, or when n is 0, I've got alpha to the 0, u of n. U of 0 is 1, so I've got a 1 at 0. And when n or when k is 1, I've got alpha to the 1, u of 1. Well, u of 1 is 1, so I've just got, if you want to think of alpha as 1/2, then I've got, 1/2. Although I'm not going to write 1/2. I'm going to leave it in terms of alpha. So this is, alpha. And so because alpha is less than 1, this thing decays like this. Okay, and it goes on forever. Now to the left of 0, because of the unit step, I've got exactly 0 over here, because the unit step is 0. Okay, so this is my plot of x of k. All I'm doing is calling the n's k's. You can call them whatever you want. But I see that in the convolution sum, the x appears with k, so that's why I'm choosing to do this. Now also in the convolution sum, I see that the h's appear with minus k. And so what I'm going to do is replace the n's with k's in the h definition, and then I'm going to flip it. Okay, so now I've got a flipped unit step. I'm going to try to draw these right underneath the corresponding samples in x. So here's 0. So I've got a flipped unit step. And I'm going to label this is h of minus k. All right. Now, we have to compute this convolution sum. Now notice, actually I'm going to back up. I can view the convolution sum then as, so a couple points here, x and h plotted versus k, right? So that's what we talked about already. Then h is flipped. Right? If we're taking the viewpoint of x and h versus k, I see that k appears as minus k for h, so I'm going to flip h. Then, look at the role of n in this equation. If I'm taking the viewpoint as if k is the variable, then n is a shift in that variable. N is the shift. These are subtle but important points that are easy to lose track of as you go through this. N is the shift, and then we're going to sum over k. Sum over k. So that really sums it all up there. So we've taken care of the first two things. Okay, so now the third point, n is the shift. Notice that if I shift by n less than or equal to minus 1. So because h is flipped, n minus 1 means to the left by 1. So if I shift at least 1 unit, this is what we're saying. Shift by n is less than or equal to minus 1. So shift to the left at least 1 unit. Notice there would be no non-zero overlap between these two signals. No non-zero overlap means when I do the point-by-point multiplication of the two signals, with h being shifted, then I get zeros in the sum. I get entirely zeros. Every term is 0. And so then when I sum up a bunch of zeros, I get zeros, and so the y of n is equal to 0. Okay, again, feel free to pause the video if you need to kind of let that soak in a little bit. All right, but we're going to move on. Now, if I shift by n equals 0, or meaning I don't shift at all, okay, the non-zero overlap, I'm going to write it out. Non-zero overlap is between, well, I only have 1 point of non-zero overlap, right? That goes from 0 to 0. And remember, this is k. K goes from 0 to 0. So between k equals 0 and k equals 0. So it's kind of a weird thing to say, but it'll make sense in a second here when we shift by something else. And what I'm trying to do is trying to find a pattern between my shift and the region of overlap, because I'm going to have to compute this sum, and I don't want to sum from over more terms than I have to. I just want to find the non-zero region. Okay, so if I shift this by 1 unit, so you can imagine, use your imagination here, but if I shift this by 1 unit, now it's here. So, and this is no longer h of minus k, this would be h of 1 minus k. So I'm not going to continue to write that. So this, I'll just say, this is 1 unit. 1 unit to the right. N equals 1 unit to the right. Okay, now the non-zero overlap, hopefully you agree with me, is between 0 and 1. So I'll write that down. The non-zero overlap is between k equals 0 and k equals 1. Okay, and if I shift by 2, I think you're going to get the idea very soon if you haven't already. You're going to notice the pattern, hopefully. If I shift by 2 units, then that would put this leading edge right here. And shifting by 2 units, the region of non-zero overlap is between k equals 0 and k equals 2, right? K, because my non-zero overlap is here to here. Okay, now the question is, for any shift n at least to 0, right? Because we know when we shift by less than -1, less than or equal to -1, there's no non-zero overlap. But if we shift at least n equals 0, then what is the pattern here? What is the region of non-zero overlap? So if we shift by n, we have a non-zero overlap between k equals 0 and k equals n, right? Here I shifted by 0 and I went to 0. Here I shifted by 1 and I went to 1. Here I shifted by 2 and I went to 2. And keep in mind what this plot is doing as I shift it. So this leading edge here is at whatever I shift by. So in general, if I shift by n, that leading edge is at n, so my non-zero overlap is 0 to n, and 0 stays fixed because we're not shifting this guy. Okay, so now I need some space, so I'm going to erase this. But notice the next point is to sum over k. So my convolution sum now, y of n equals, and remember this is for n greater than or equal to 0 now, because less than or equal to -1, the output was 0. Okay, so I have this convolution sum, x of k, h of n minus, boy, we're in the nitty-gritty details now, I love it. Okay, so we're not going to sum from k goes from -infinity to infinity because a lot of those terms are 0. We only need the non-zero overlap. Well, what's the non-zero overlap? Well, it depends on what n is. And for any n in this range, we're going to sum from k equals 0 to k equals n. That's what we just decided. Okay, so my bounds are shrunk to k0 to kn because everything outside of that range is 0. So this becomes x of k, h of n minus k. So I'm going to compute this sum directly now. In this non-zero range, what is x of k? Well, here is the mathematical equation for x. Right, of n, but we know we can swap the n's with the k's. So I can just write alpha to the k, and I'm going to just drop the unit step because the unit step is either 0 or 1, but we know we're in the non-zero region. So in the non-zero region, the unit step is 1, and so I'm just going to drop it. Okay, next I have in my sum h of n minus k. So here's the mathematical equation for h. Okay, and so I know again that in this region, the unit step is just either 1 or 0, and we're dealing with the non-zero part of this. So the unit step is just 1, and So I'm just going to drop it. It's 1. So now I've got this thing, and I need to evaluate that. Okay, I'm going to erase some of this. I need to evaluate this. So how do we evaluate that? Well, you might recall from mathematics, and we're going to need this quite a bit. So if you are making a list, a sheet of equations that you're going to need, this would go on this list. There's the partial sum formula. And it's called partial because this top bound right here does not go to infinity. There's a different formula for when that goes to infinity. The partial sum formula in mathematics says that the sum k0 to n of alpha to the k, so this is perfect. I mean, our equation is exactly in this formula, is equal to 1 minus alpha to the n plus 1 over 1 minus alpha. And so long as the magnitude of alpha is less than 1. Okay, and so we know that the magnitude of alpha is less than 1. In fact, we made an even stronger constraint at the beginning to say that alpha is between 0 and 1. Actually, no, back up. I'm sorry. This holds for any alpha. The partial sum formula holds for any alpha. Okay, so we evaluate this, and we've got 1 minus alpha to the n plus 1 over 1 minus alpha. And so this is it. And I just erased it, unfortunately, but recall that this was only true for n is greater than or equal to 0. For n less than or equal to minus 1, we had y of n was equal to 0. And so if we combine those things, we can write it piecewise. We can say y of n equals 1 minus alpha to the n plus 1 over 1 minus alpha, n greater than or equal to 0, 0 else. Or, even slicker yet, we can write y of n equals 1 minus alpha to the n plus 1 over 1 minus alpha times the unit step. This is preferred because it's just one equation. And why is that true? Because remember, when n is less than 0, the unit step is 0. So this is 0 times, whatever this is, which is 0. So this is the answer. This is the answer. Okay, so let's plot it. Let's make a plot. I'm running out of room again. Okay, I'll try to plot it down here. Okay, here's the origin. Okay, so just to be able to visualize this, let's pick let's not pick an alpha. Okay, at 0, I have 1 minus alpha to the 1 over 1 minus alpha. So that's 1, and the unit step is 1. So at 0, I have 1. Now to the left of that, because the unit step is 0, I have 0. Remember that when n is less than 0, I've got 0. Now, what happens as n goes to infinity, alpha to the infinity goes to 0 for this reason. Because think of 1/2, 1/2, 1/4, 1/8, so that goes to 0. So I approach 1 over 1 minus alpha asymptotically. So we'll see something like this if we plotted this. Where this asymptote is 1 over 1 minus alpha. Okay, and it just keeps going like that. It gets closer and closer to that value. Okay, So again, this is y of n. That's the solution to this problem, this convolution problem. So let's summarize, because it's easy to get lost in the mathematical details. Do not get lost in the math. Keep your focus on engineering. What we did was we found the output of this system. So we found a voltage or a current or whatever, a vibration or whatever. When we input this signal, shown here, into the system, this is what we get out. And the reason we don't have to perform any circuit analysis or any mechanical analysis is because we are given the impulse response. We're given how the system responds to just a quick little disturbance. So given that response to the quick disturbance, and given the input, I can just perform the convolution and I know what I'm going to get out. Amazing.